Sorry for the delay, guys. Just having a rough morning. Okay, I think we're live. Okay, so let's start with probability and counting. And hopefully this will help you with your quiz, the upcoming quiz. I think this is kind of a fun topic, but it's not easy. So let's do a little more practice. Okay, so the first question, what is the probability of getting more heads than tails on 4 tosses of a fair coin? Any ideas on how to start? So first of all, I think the more important thing is, I think the first thing you should think about is like, what does it mean by having more heads than tails? Like, how many heads do we need to have more heads than tails if we are tossing a fair coin 4 times?
We'd need
3 or
8 or more
4.
heads.
Yes, exactly. So we need 3 or 4 heads, right? So basically must toss 3 or 4 heads. Okay, so after that, what do we do? So how many different combinations do we have total? If we're tossing a coin 4 times, how many, what's the sample space? So if I say, let S be the sample space.
It's 2 to the 4.
Yep. Why is that?
Because at least if you're doing it with orders, which makes it simpler, then each flip is a place in the sequence of flips and can have 2 values.
Right. So it's something like this, right? You have 4 spaces, and then each one is either head or tail, right? So you have 2 choices. Yep, for each space. So that's 2 to the 4th. So then we already know the size of the sample space. So now, how do we get? You already said that to toss more heads than tails is 3 or 4 heads, right? So can we compute the number of possibility of tossing 3 or 4 heads? How do we do that?
So since it can be any order but the same number, you have to multiply the probabilities of the independent events and then also multiply by the number of possible orders that those combinations of events could happen. Oh wait, no. That's a different path that you go down. We're going down a different one. So the number of possible ways it could happen is with 3, and then with 4. And with 4, there's only one way of it happening. And with 3, there's 4 choose 1 possible ways of it happening.
Yep. So why is it 4 choose 1? So this is what, 4? No, 3 heads, right?
Yeah. It's because you're choosing one spot for where the tails is out of the 4. Yeah.
Yeah, exactly. And that is actually the same as this. There's no difference between these two. You can use either. And then the other one is just one way, right? So 4 tosses, 4 heads. So there's only one way.
Yeah.
So yeah. So the other way that you were talking about is also correct. You just need to be a little careful and not mixing them up. So like if you're computing probability, that's different from computing the counts.
Yeah.
Yeah. So that is actually 5. So then what do we do? Oh, I made a mistake here. It's N of S. So what's the probability of E?
You take the count divided by the sample space.
Yep. So that's 5 over 16. Make sense? Any questions? No? Okay. Let's keep going. If the Bisons have a 3/5 probability of winning any given game against the Mustangs, what will be the average length of best of 5 series between these two games? Between these two teams, not two games, between these two teams. So remember, there's a typo here. This is actually 1. Okay, the number of games played until one team has won 3 games, right? So how do we approach this problem?
So basically you have to get the probabilities of each length of the game.
Yeah, exactly. So how many different lengths can there be for a best of 5 series?
3, 4, and 5.
Exactly. Okay, so then let's write this formally. Let X be the length of a game. We know that a best of 5 series game can be of length 3, 4, or 5, right? So that's the first step. So then E of X is what? Three times what? Probability of what? Anyone?
Of 3, winning 3 games.
Yes. So not winning 3 games, but like length is 3. So let's just write X is equal to 3 plus 4 times probability of what? Same thing, right? X is equal to 4 plus 5 times the probability of X is equal to 5. Okay, so the harder part is to actually compute these probabilities. Any ideas? So how do we compute? I'm going to write them separately. So how do we compute the probability of X is equal to 3? When does it, how does the games look like if the game ends in 3 games? If the best of 5 series ends in 3 games?
Either Bisons win all 3 or Mustangs win all 3.
Exactly. So can you compute the probability of that?
Yes, that'd be 3/5 to the 3rd. And then for Mustangs, it'd be 2/5 to the 3rd.
Yep.
So that'll be plus. Yeah.
Exactly. So that's with 3, right? Okay, so what about the probability of X is equal to 4? How do the games look like with length being 4?
And that'd be 3/5 to the 3rd plus 2/5, just to the power of 1.
Times,
And then,
right?
yeah, and vice versa with plus 2/5 to the 3rd times
Right.
3/5 to the 1.
Right, but you gotta remember you need to there are different ways of picking. Okay, so let's first of all look at how the games look like. So with X is equal to 4, I'm gonna wait, actually, do I have extra space? Okay, I do have extra space, so that's good. So with X is equal to 4, we have something that looks like 1, 2, 3, 4, right? But then it has to either look something like Bison, Bison, Mustang, Bison, right? Or Mustang, Mustang, Bison, Mustang. So that means the last spot doesn't really have a choice. The last one has to be the winner, right? So then you're only choosing from the first 3. And then for the Bison case, you're choosing 2. Bison has to win 2 games out of the first 3. And for Mustang to win, Mustang has to win the first 2 games out of the 3. Not first 2 games, but like 2 out of the 3 first games. So that means we're choosing 3 out of 2 or 3 out of 1, whichever. It's the same thing. And then multiply by their 3 Bison wins 3 games. So 3/5 to the 3rd times, and then Mustang wins 1 game, right? And then it's the same thing on this side. 3 choose 2. Mustang wins 3 games and Bison wins 1 game. Does this make sense to everyone?
Yep.
Okay, awesome. So can we keep going? What is the
Can you go back
probability?
just for a second? I'm still
Yeah.
writing it down.
Yeah, no problem.
All right, thank you.
Okay. So can we keep going? The probability of x is equal to 5. What does this one look like? Very similar to the one that we just did, right?
So this be 4 choose 2.
Uh-huh. So 1, 2, 3, 4, 5, right? So still the last one, if Bison's gonna win, Bison has to be the last one to win. So this position doesn't have a choice. So it's something like this, right? Or the other way around. So 4 choose 2, right? We're choosing 2 positions out of the first 4 for Bison to win. And then what happens after that?
3/5 to the third times 2/5 squared.
Yep. And then the other one is the same thing. Right, C of 4 choose 2. Mustang wins 3 times. The Bison wins twice. So the other way of getting this probability of x is equal to 5, you can also think about the complementary problem. So we already know that the game of a best of 5 series has to be 3, 4, 5. There cannot be any other lengths, right? So we already found the probability. So we want to find the probability of x is equal to 5. So then we already know these two, right? We already know the probability of x is equal to 4 and x equal to 3. And then we know that these are the 3 possibilities we can have. We cannot have more possibilities. So that means we can do this, right? So either way, it's fine. You get the same answer. Okay, so then E of x would just be putting all of that together, right? So 3 times probability of 3, x is equal to 3, plus 4 times probability of x is equal to 4, plus 5 times the probability of x is equal to 5. So that together would give us 4.0656, something like that. Any questions about the problem?
Why do you multiply each probability by the length?
By the length? What do you mean the length? You mean
Like you have like 3 times the probability where the length is 3.
Oh, this is to compute the expected value. So that is the the expected value formula. But intuitively, it's like you have the probability of it being 3 here, right? And then you have the probability of it being 4. So basically you're weighting each probability. You're saying that the probability of it being 3, and then you're weighting it to be 3. You're weighting it to have a 3 weight. So then you can imagine like when the length is 5, the game is longer. So that should kind of increase the average length. So this is the expected value is basically the average, right? The average length of the game. I don't know if this makes any sense. So it's like normally if you have, how do you compute an average of a okay, so it's like this, right? We have 3, 3, 4, 4, 5, 5, 5. We have this list, array, whatever you want to call it. So how do you compute the average of the list?
Add them all up and divide them by the length.
Okay, so that's good, right? So you add them all out divided by length. So how else can you do it? You want to compute the average, so let's also call this E of X, average. So 2 out of the 1, 2, 3, 4, 5, 6, 7 is 3. Uh, 2 of the 7 is 4. 3 of the 7 is 5. Do you see that this is the same as what you just said? 3 plus 3 plus 4 plus 4 plus 5 plus 5 plus 5 over 7.
Would it be equivalent to not multiply each probability by the length and then just divide them by the total amount of games?
But do you know the total number of games?
No, I'm just trying to see like if that would be equivalent.
I think if you do know, like in this case, it would be equivalent, but if you don't know, because how would you know like the total number of possible games? You can do a counting problem and add them up. This is like weighted average, basically. Does this make sense that this is the same as this right here?
Yeah, that makes sense.
Yeah, and then do you see how this is the same as this formula right here?
Yeah, I can see that.
You're using the length times the probability, length times the probability, or weight times the probability. In this case, the length of the game is that weight. Does this make sense to everyone or not really?
It kind of makes sense to me.
Yeah, it's
Yeah, I
just
think
to
I'm starting to
compute.
get it.
It's just to compute the average. It's just that this is the weighted average, so there are repetitions in your list, right? Because there are multiple ways of having games of length 3. There are multiple ways of having games of length 4. So you have to kind of multiply the probability of that with the weight together. So if you do know the total length of the game, you can. So I think the hard part is that, I think it's much easier to compute the probability than to say that how many games there are that are of length. You can do that, actually. You can. So you can compute how many games there are of length 3. And then you multiply that by 3. And then you add how many games there are of length 4. You multiply that by 4. How many games there are for length 5? You multiply that by 5 and divide all of this by the total number of possible games. You can do that too, but I think this is a much easier way to think about the problem. I think we're going to see a few more, and then we're, is this one? Yeah, we're going to see a few more, and then I think we'll understand a little bit better. So let's look at this one. this one should be a easy one. What is the probability that when a pair of 6-sided dice are rolled, either or at least one die shows a 5 or the dice sum to 8? What are the two events here and what should we do?
The two events are one die shows a 5 or at some state.
Okay, so let E1 be the event that one die, or at least one die shows a 5. Let E2 be the event that the dice sum to 8. Okay, so what are we computing? We're computing E1 or E2, right? The probability of E1 or E2. And how do we do that?
Isn't it probability of E1 plus probability of E2 minus probability of E1 and E2?
Yep, exactly. And that is called the general sum rule, I think. Yeah, general sum rule. Why is that though? Why do you think that is?
Because you can roll a 5 and a 3, and it both has one die as a 5 and sums to 8.
Right, exactly. So you're saying that there's some overlaps between the events, right? So if this is E1, this is E2, the two circles, there's some overlap right here. So when you add them, you double counted the overlap. So then you have to subtract it. Okay, so how do we compute the probability of E1? E1 means at least one die shows a 5, right? There are only 36 options.
Would it be 2 times the probability of one die being 5?
But yes, but there's also, it's the same thing, right? You would have 5, 5 that show up in both. If you do this, one die being 5, the probability of one die being 5 is 1/6, right? So 2 times 1/6. But then this shows up in both cases. When you're counting the first die being 5, this shows up. When you're counting the second die being 5, this also shows up. So what do you do now?
Subtract 1 over 36.
Yep, exactly. So that is the first part. So what about the second part? Die sum to 8. What are the possibilities? What are the combinations?
3, 5, and 2 and 6.
Yep, 3, 5, 2, 6. But then there's also 4, 4, right? But then these two you can flip them over. 5, 3, and 6, 2, right? So they're 5 out of 36. Okay, what about them happening together? E1 and E2. The probability of E1 is E2 is what? When do you have an overlap? I think Justin said it.
It's 5, 3, and 3, 5.
Yep, okay. So that's minus 2 over 36. And that gives us 11 over 36 plus 5 over 36 minus 2 over 36. And that is 14 over 36, 7 over 18. Any questions? So I think whenever you see like 2 regular dice, if you want to verify if your answer is correct, just write the 36 pairs out and then actually circle the ones that make sense and then see if you get the same answer. This is one of the easier problems, I think, because you can always check. Okay, let's move on to the next one. So we're doing expected value again. So hopefully this time we can make more sense of it. A player pays $10 for the privilege to play a casino game. The player tosses a die 3 times with the following payoff: $10 for the first die that shows 6, an additional 15 for the second die that shows 6, and an additional 20 for the third die that shows 6. So what is the expected amount of money the player will win playing the game 1 time? So what are the 3 types of events that could happen here? How much money could a player possibly win in a game?
You can make up to $45.
Right. Okay. So what are the 3 different ways to win?
Through any die roll being a 6.
Okay. So then if the player rolls 1 die, how much does he win? Like if the player rolls 1 6, how much does he win?
He gets $10.
Okay. So $10 for 1 6, right? I'm going to write 1 6. Okay. So 2 6. How much does the player win if he or she rolls 2 6?
$15. No, 25 total.
Yep, $25 for 2 6, and then 3 6.
For 3 6, they get 45 total.
$45 for 3 6. Okay, so we're gonna do the same thing, right? So these are the weights, and then we need to time the probability of getting these weights. So let X be the amount of money the player wins in a game. Then the expected value of X is equal to 10 times the probability of X is equal to 10, which means rolling 1 6, right? So, or like 1 6. And then 25 times the probability of X is equal to 25, which means 2 6, plus 45 times the probability of X is equal to 45, or 3 6. Does this make sense? You kind of starting to see how it works? You're basically saying like how much, like how important is this value to the average? That's kind of what you're saying. Like if this probability is very small, you know this value shouldn't play too much into the average. And then if you have a probability that's large, then you know that this value comes up very often. So it would have like a more important role in the average. So it would be more important when for the average value. Kind of carves out like a bigger chunk for the average. So how do we compute each of these probabilities? So probability of, that's right, probability of 1/6 is what?
1/6.
1/6 is, okay, 1/6 is you roll a 6 once in one roll, right? How do you roll 1/6 in 3 rolls?
That'd be 1/6 times something over 36.
Think about it. Just continue with your thought process. So 1/6 is the first roll. Let's say you roll a 6, and the second roll you need to roll something else.
Could you do choose 3-1 times 1/6 times 5/6 to the 2?
Yep, that's exactly right. Because you have to roll something that's not a 6 for the second roll and the third roll, or like just other 2 rolls, right? You roll it once, and that's a 6, and then the other 2 times you have to roll something that's not a 6 for it to just be 1/6. And there are 3 different ways of arranging this. So what about the probability of 2/6? Same logic here.
Choose 2 from 3 times 1/6 squared times 5/6.
Yep, exactly. So same thing here. You're going to get 2 6 and then 1 something that's not 6. And then 3 6 is what?
Choose 3 from 3 times 1/6 to the third.
Yep. And there's only one way of doing this. This is 1. Yeah. So now we just add them together. We go back to the same thing. So whenever this happens, this event happens, we get $10, right? So 10 times the probability of 1/6. Whenever this happens, we get $25. And whenever this happens, we get $45. And after we add them all together, we get 5.42, something like $5.42. So that's why we shouldn't, I don't know, shouldn't, spend too much money at the casino, because most of the time you'll probably lose, because you have to pay $10 to get in the game, and then you only win $5 back. Expected value. Obviously, you can win 45 sometimes. Okay, so the second question is, how much can the casino expect to make if 10,000 of these games are played each day? What do we do? So on average, how much can a player win during one game?
$5.42.
Right, but remember they also have to pay $10, right? So on average, a player wins this much, right?
Could you do 10,000 times 10 minus 10,000 times $5.42?
Yep, that's fine. So 10,000 times 10. Oh, you say 10,000 times 10 minus 10,000 times 5.42. Yep, because this is the amount that the players pay during 10,000 games. And this is the amount that the casino pays the players. Right, so this is casino to player. This is player to casino, right? So we get $45,800 a day. That's a lot of money. Any questions about this? Does this make sense? Okay, no questions. Oh, we have another one. It's just never ends. Okay, suppose a 3-person committee is formed for a club by drawing names out of hat. If the club has 30 juniors and 20 seniors, what is the expected number of seniors on the committee? So how many different numbers of seniors we can have? I think the first thing is always to think about the possibilities, like how many different possible outcomes can we have? When we compute expected value, that's the first thing you should think about. How many different types of outcomes
You can have 1, 2, or 3, or 0 seniors.
Exactly. Okay, so 0, 1,
Although
2,
0 seniors contributes none to the average.
Right, exactly. 0 senior contributes nothing to the average, so we don't have to compute it in the expected value, but still, if let's say we do the same thing, let X be the number of seniors on a committee, right? Then expected value of X is 0 times the probability of X is equal to 0, 1 times the probability that X is equal to 1, 2 times the probability that X is equal to 2, and then 3 times the probability that X is equal to 3. And this is 0, right? So disregard it. So now we have these 3. How do we compute each one of these? How do we compute the probability of having 1 senior on the committee? I think this for this one, it's like easier to think of them as counting. So you're choosing how many from how many. So we're choosing, kind of think about the sample space and then the events. So we're computing the number of ways to, the probability of having 1 senior on the committee, right? So how many different ways can we choose 3 members out of everyone?
Choose 53.
Right, so 50 choose 3, right? So we're choosing 3 people out of 50 people. So how many different ways can we choose 1 senior out of 20?
Would that be C21?
Yep, 21. And then what about the rest of them? What do we have to be? Who do they have to be?
The rest would have to be juniors.
Okay, so what does that mean?
Would that be C32?
Yep, exactly. Okay, so can we keep going? 2 times what? Probability of X is equal to 2. And how do we compute X is equal to the probability of X is equal to 2? Same thing, right? You always divide by the sample space. But then what about the numerator?
You'd be picking 2 from 20 and then
Uh-huh.
30.
Yep. 2 from 20 and then 1 from 30. Okay. And then 3 times last one here. Same thing, right? So this one is just we're picking 3 seniors from the 20 seniors, and then we also have this. So that gives us 1.2 seniors. So we can expect 1.2 seniors on the committee. Make sense? Any questions?
If we're gonna go the other way, can we do something like, for example, 1 senior, we can do 2/5 times 3/5 squared?
Yes. But then 3/5 squared, right? But then how many different ways? You have to multiply by how many different ways?
1. Oh, I think C31.
Yep, exactly. So 1 times that.
Okay.
And then for the 2 case is 2 times.
C32.
Yep. And then you're choosing 2 seniors,
2/5
right?
squared and 3/5.
Yep. That's exactly right. And then you just keep going.
Right. I was thinking like, the order doesn't matter here, but I'm still thinking, why are we using C31 here?
Because if you're choosing 1 senior, right, you can have like there's 3 spaces.
Right.
You can choose
Like which one first, and
you can choose like senior first or senior here, or like basically the order is that who do you choose first type of thing.
okay.
Yeah.
Yeah. Thank you.
Yeah. It's like thinking about the if you think back to the games, right? It's the same thing. Like
Oh, I get it now.
Yeah.
Yeah. I think the game makes more sense here.
Yeah, I think
than choosing people.
Yeah, because here you think that order doesn't matter. How come that we have 3 people in the committee? But in the game, it's the same thing, right? You always win no matter where the 2 spots are, or like how many, where the wins are. You always win, but still we care about when they first win or second win. Yeah. Okay, so we're probably just gonna. This is like a pretty hard problem, but I think it's kind of fun. And then I hope that I can explain it well enough for people to understand. But let's try it. So in how many ways can 4 married couples be seated at a round table so that the spouses sit together? Any ideas?
So I guess you pick a spot for one spouse, and then there's 2 possibilities, one where the other is to the right of the one spouse and one where they're to the left. And so I guess if there's 4 seats, then you have 4 spots for the one, and then you multiply that by 2. So you have 8 spots. 8 possible arrangements. If that makes sense.
Yeah, I think you are on the right track, but there are actually a lot more than that. So
Oh, I see. So
yeah.
that's the number of possible places for picking the spouses, and then you pick the possibilities for filling in the remaining 2 seats and multiply the 2 together.
I think that's almost right. So 1 second. Let me see. Okay. Hopefully I can explain this. So let's just, let's just assume there's husbands and wives. Okay. There's 4 couples are husband and wife. So we have,
Oh, it's 4 married couples, not 4 seats. Okay.
yeah, it's 4 married couples. So H1, W1, H2, W2, H3, W3, H4, W4. So you can imagine the problem with a round table, that the hard part about being in a round table is that, if you have an arrangement and then you flip it, the mirror image would still be the same. And then if you rotate the table, it would still be the same as well, right? If you rotate the table, the arrangement would actually be the same.
So do you divide the total number of arrangements by the number of possible like rotations and then divide that by 2 for flipping?
I think that is very, wait, actually, there's probably more to be divided. So we generally, we avoid these. We just kind of count the ones that would actually happen, that would be different. Yeah. So first of all, let's think about it like this. If we pick one spouse from each pair, we pick 4 people. How many different ways can we pick one spouse from each pair?
So that would be and leaving a space between them, right?
It doesn't matter, right? You can insert 2 people there too. Like, so that's the thing. If let's say you have a round table and then you pick like H1 and then W2 and then W3 and then H4, like you can insert 2 in here, right?
Yeah.
You can have 2 seats there. Like, that's fine. But we're just picking 4 first. Let's pick 4, 1 from each pair. First, pick.
Okay, well that would be would it be 8 choose 4?
If you're using 8 choose 4, then you are choosing any random 4 from these, right? But we want 1 from each pair.
Okay, I see. So I guess the number of ways to pick 1 from each pair is 2 to the 4.
Exactly. So there are 2 to the 4. So this is the same thing as having 4 spaces, and then each has 2 choices, right? So either you choose the husband or the wife, right? So there are always 2 choices for each of these 4 spots. So there are 2 to the 4th number of ways to pick the first 4. So let's say that we pick something like the same thing, H1, W2, W3, and H4. So, because it's a round table, so let's say that we seat the first person. We seat him first. We seat him right here. So then you can imagine if we want to place these 4 people on the table, you just need to determine who's going to be on the left and who's going to be on the right, right? Because the other person, this last person, doesn't have a choice. As long as you determine these 2, this last person would just be the last person in the 4. Right?
Yeah.
But then you also have to remember that if you pick W2 here and then W3 here, that's the same thing as flipping them over. So that's the same thing as if we have H1 here and then we have W2 and W3, right? And we have H4 here. That's the same thing as, so these 2 are the same, right?
Yeah.
So how many different ways can we arrange these 4 people? So we already seated the first
person. So I
person.
guess, yeah, so you pick 1, so that's 4, and then you multiply that by 3 choose 2, because it doesn't matter which one is on the right or on the left.
Exactly. So we have to consider them
the last one is determined. So you have 4 times 3 choose 2.
Right, but then that's the hard part, right? So we have 3 choose 2 number of ways to placing the left and right people. The problem here is that you cannot multiply by 4. Like this. So how do you think about it? Like, you can pick any one of them, and there are still only 3 ways to arrive at the same arrangement. Like, for example, if the first person you picked is W2, you still only have 3 arrangements to arrive at the same exact arrangement if you picked H1 first. There's only 3 ways to arrange these 4 people in a round table.
Okay.
Does that make sense? It doesn't matter who you pick first. You always have 3 ways to arrive at the same 3 arrangements.
That makes sense. Yeah.
So we only have 3 choose 2 ways to arrange these 2 people, or arrange these 4 people in a round table. So now we have to put the spouses in, right? And we want them to sit together. So then basically we're going to do something like this, right? W4, H2, W1, and then H3, right? We can either do this. So we just filled them out. So put everyone on their spouse's left side, right?
Yeah.
We can also do them the other way around. So we put everyone on their right side. And there are just 2 ways of doing this.
So it's just 3 choose 2 times 2. Okay.
Times this.
Times that. Yeah.
So why do you think we can't insert 2 people here? Why do you think we can't say that, okay, H2 belongs here and W1 belongs here? Why do you think this choice is already included?
Once you pick H2, W1 has no other place to go, right?
You can actually insert 2 places here. That's allowed. It's a round table, right? Just say that. Have 1 more seat here. But we already
It's already
counted
included
this.
because, yeah, we already counted picking each spouse from each pair.
Right, exactly. So this is the same thing as picking. So like in the first step of picking 1 from each spouse, we picked W1 instead of H1. So imagine if the first step that we picked W1, so we picked W1, W2, H4, and then W3. If we picked these 4 first, that's the same thing, right? That's exactly the same thing as inserting W1 here. Because then you just have this. Right? And you actually arrive at the same arrangement. So the answer would be 2 to the 4 times 3 choose 2, which is just 3 times 2, because you just fill it in either on the left or on the right. It's probably going to take some time to think about. We're running out of time, but like I hope this makes a little bit sense, and
it's starting to make sense to me.
And I think it just takes some time to think about. I definitely stared at the problem for a while last night. And then yeah, I hope this is kind of like a fun thing, sort of. I hope you.
It's like definitely not the type of structure that we've dealt with in class.
And then I don't think there's gonna be anything like this on the quiz. It's just a little fun problem that hopefully you guys would like to think about a little bit. Okay, but that's the end of the discussion. Hope you guys have a good day.
It goes to show that you have to there's always going to be problems that you have to actually think about that don't just follow the simple formulas.
Yes, and I think that's the biggest thing about studying something like this, right? It's like math-related things, is to train your brain to think in a very logical way. Yeah. And I think that's the most important thing. Whether or not you do anything related to math or computer science in the future, I think that's still very, very important. So
yeah.